So good afternoon, and thank you all for joining us, hopefully for some of you during your lunch hour. My name is Charlotte Hudson, and I direct the LenFest Ocean program. And if you're interested in learning more about our program, you can find us online at lenfestocean.org or on Twitter at lenfestocean. So today we're thrilled that Dr. Tyler Eddy, who is now a postdoctoral fellow in the Nereus program at the University of British Columbia, has joined us to talk about some of the work he did with the LenFest Ocean program funding. Tyler completed this work while he was at Dalhousie, working with Dr. Heike Lotz. So in a series of recent papers, Tyler and his colleagues found that many invertebrates play important roles in marine ecosystems. Tyler will talk a little bit about the results of his recent work, which touches on lobster fisheries in New England and Nova Scotia, and on global patterns he found using ecosystem modeling. So Tyler's going to speak for about 30 minutes, and then we will have time for questions. And as a reminder, if you're surprised that we don't hear you, all of your lines are on mute except for Tyler's to prevent any background noise, and then we will use the Q&A box on your screen for questions, which my colleague Dana will describe after the presentation is over. So now I'm going to turn it over to Tyler, and thank you.
Thank you for that introduction, Charlotte. Okay, here's the first slide. We're good. So I can't actually see who the participant list is, so this is the first time I've done a blinded presentation. I mean, we all do this in the peer review process when we submit articles. We don't know who's actually reading them, but this is the first time I've done a blinded presentation, so hopefully I'm going to hit the kind of right level of expertise for the audience, and if there's any kind of details that you're curious about, you can ask me after the presentation. As Charlotte mentioned, this is some work that I did while based at Dalhousie University in Canada, working closely with Heike Lotz, as well as Beth Fulton, who's based at Cairo in Australia, and Marta Cole, who's now in Spain. And we had a number of other collaborators who we invited to work on the project who were kind of experts on local ecosystems. So the structure for the talk today, I'm going to do a little bit of an introduction about the global expansion of invertebrate fisheries to kind of set the stage for this research. And then I'll touch briefly on the ecosystem approach to fisheries and the ecosystem modeling approach that we used. Then I'm going to talk about the results from our research about the ecosystem effects of invertebrate fisheries at individual locations around the world, as well as what we sort of found when we synthesized these individual locations together. Then I'm going to talk a little bit about some simulations that we did with some of the models, asking some more specific questions related to ecosystem-based fisheries management. And then, as mentioned, there'll be some time for questions and discussion. So I'm originally from the South Shore of Nova Scotia. This is a picture of La Have, Nova Scotia from the 1940s. And it's kind of hard to see what's going on here. The resolution isn't great. But this is actually a codfish, which is being preserved through the salted and dried methodology. So this primarily was the main fishery in Nova Scotia and much of Atlantic Canada, and played a large role in the history of Europeans coming across the Atlantic and settling in North America. However, we now know that Newfoundland especially, but this region in general, has seen major changes in the fisheries that are operating, which is sort of the most infamous is the collapse of the cod fishery. So now we still have a commercial moratorium on cod in much of Newfoundland, and we're seeing that we're no longer seeing these species in the abundances that used to occur historically. So not only did this have implications for the ecosystems of this region, it also had strong implications for all the communities that had depended upon these fisheries for their livelihood. So we saw lots of little outport fisheries throughout Newfoundland and Nova Scotia start to dry up as a result of these fisheries collapses. In recent years in Atlantic Canada, we've seen the fisheries change. So now in Nova Scotia, you hardly ever see any cod being landed, and the primary fishery in Nova Scotia is for lobster, American lobster. And in Newfoundland, they're also catching a lot of invertebrate species, a lot of crab species. And this sort of trend has been sort of observed in many different places, not only in Atlantic Canada, but globally as well. So here I'm showing a figure of the catch of different invertebrate fisheries from the 1950s up until 2012. And we can see this increasing trend in a lot of these different groups, especially crustaceans and cephalopods. And we've sort of seen that these levels have leveled off in recent years. And this is a global map showing the amount of catches that are coming from different large marine ecosystems, or LMEs. And we can see that in Atlantic Canada, the darker colors, the darker blues, are indicating greater catches. And as well as New England, we're seeing quite high catches of invertebrates. Similarly, in some regions of Asia and Europe and South America. So this is not only localized to the northeast part of North America. We're seeing these trends occur at other locations around the world as well. So a few sort of statistics about invertebrate fisheries as a little bit of background. So in 2012, they comprised 14% of the global fisheries catches by weight. Crustaceans have been the most highly valued fish group since the 1970s, and they were worth approximately $3,000 per metric ton in 2005. In both New Zealand and Canada, Nova Scotia particularly, lobster is the most valuable export fishery. I'm going to speak a little bit more to those examples later on in the presentation. And in the United States, only 42% of the 89 federally managed invertebrate stocks are assessed, compared to 79% of the 388 finfish stocks that exist. And it has been acknowledged that there are challenges in developing age and growth data. So some of the life history characteristics of invertebrates and the fact that they don't have otoliths makes it a little bit difficult, and that can be part of the reason explaining why they're not assessed as much as finfish. So the motivation of this work really stemmed from this paper that Heike Lotze and Sean Anderson, along with colleagues, published in 2011. And they're really looking at this rapid global expansion of invertebrate fisheries. And following collapses of, for example, Atlantic cod in this region in Atlantic Canada, we really see these invertebrates being targeted in different regions. So they wanted to sort of document this expansion and look at some of the trends and drivers. So on the figure that I'm showing now, showing a range of the different invertebrate species that are fished, and we can see that they occupy a range of different trophic levels from top predators down to herbivores. And on this matrix, we can look at some of the different roles that they play within ecosystems. So both predator and prey, detritivores and scavengers, herbivores, filter feeders, and then we also know some invertebrates can be important for habitat-forming species, such as oysters in the Chesapeake Bay, for example. So really, this paper sort of did a global analysis of these expanding fisheries. And what we wanted to drill down on this LandFest project was starting to look at what are the roles played by these different invertebrate groups within ecosystems, and what happens when we fish them, what happens to the rest of the ecosystem. Now, this is another interesting figure that was produced in that same paper, and this is showing the year that sea cucumber fishery started on the horizontal axis compared to the distance from Hong Kong on the vertical axis. And this is basically documenting a serial depletion of sea cucumbers globally. So as closer markets to Hong Kong become depleted in the early part of the time series in the 1950s, we see these fisheries expand globally farther and farther away from the main market. So this is kind of the following on from the overexploitation of some finfish species, which happened a little bit earlier in history. We're seeing similar kind of trends happening now for particular invertebrates. So the aims of this research were to characterize the ecological roles among invertebrates within ecosystems, to test the ecosystem effects of invertebrate fisheries, to test different ecological indicators to explain effects, to see if we can come up with some sort of general understanding of different invertebrate groups. And then the ultimate goal is to provide information for fisheries managers and policymakers to inform sustainable and ecosystem-based management of invertebrate fisheries and conservation of higher trophic level species. So hopefully throughout the remainder of this presentation, I'll be able to address all of these aims. So I was informed that the audience is probably up to speed on the ecosystem approach to fisheries and ecosystem modeling, but just a little bit of a background here. So really we want to know not only what impact a fishery is having on the species of interest that it's targeting, but also what are the impacts on everything else in the ecosystem. So we're interested in the connections among the different species. And the ecosystem modeling approach that we used was called EcoPath with EcoSim, which was developed at the University of British Columbia. And their motto has been no fish is an island. So recognizing that all these different species are connected together through the food chain. And if we remove one species, it could potentially have impacts on a number of other species within the food web. And also acknowledging that these different species interactions can contribute to natural mortality, and we need to differentiate that from fishing mortality. So in single species fisheries management, natural mortality is often a constant, and we're really interested in trying to figure out the fishing mortality to produce maximum sustainable yield. In this ecosystem approach, we're recognizing that the natural mortality can change given the fact that predator and prey roles are important in controlling the abundance of different populations. So the ecosystem modeling approach to fisheries has been used quite a bit in the fisheries literature recently. There's been a number of high-profile papers that have used EcoPath with EcoSim models, including the 2009 Worm et al. Science paper. And in this paper, they were exploring some alternative management targets, such as multi-species maximum sustainable yield, which is shown here in the blue curve, and I'm going to speak a bit more about that later in the presentation, as well as some work that was led by Tony Smith, looking at the impacts of low-trophic level species on marine ecosystems, or more commonly known as forage fish. And they also used ecosystem modeling approach to start to look at these impacts on ecosystems more generally. And I'm going to touch on that study a little bit later in the presentation as well. Just a bit of a background on the ecosystem modeling. One of the models here that we used, a model that I developed during my PhD in New Zealand, was based on a temperate coastal ecosystem. And this is basically a food web, and you read this by trophic level on the vertical axis. So we have all of our primary producers at the first trophic level, and then all these different linkages through the different groups are feeding linkages. So this is basically a who's eating who. And the idea with the fishery simulation is if we, for example, fish lobster from this food web and we pull some of the lobster out of the system, we can think of this as a spider web, and it's going to have impacts on all these other different species that it's connected with, either directly or indirectly. So this was the ecosystem that I'm sort of most familiar with. I did a lot of diving in this ecosystem throughout my PhD, and a lot of that survey information informed the ecosystem modeling. So this is Wellington on a relatively calm day. The Cook Strait can be quite rough. If any of you have ever been there, you can probably attest to that. So trying to collect all this information about all these different groups within an ecosystem, at some times it feels like you've got everything going well and everything is in control and you're collecting all the data you need. And other times it feels like it's a bit overwhelming and you might never get your model balanced if you've ever been through this process before. So basically these are really data intensive models. They require a lot of different parameter estimates for a lot of different species groups in order to sort of make this approach possible. So that is one of the limitations of the approach that we used here. But if you are able to come up with an ecosystem model, you can start answering some interesting questions. And one of the questions we looked at closely in this New Zealand ecosystem was, what is the ecosystem role of lobster, and how has that changed over time? So I'll direct your attention to the plot on the top, which is showing vulnerable biomass of lobster throughout time. So here we're looking from 1945 up until 2012, and you see a decrease of about 80% in the biomass of lobster over that time series as a result of fishing. Then we can do a historical reconstruction of this ecosystem from the beginning of the time series in 1945. And then we can also compare that to the present day version of the ecosystem in 2008, when biomass of lobster was reduced by about 80%. And looking at an index which is referred to as the Keystone Index, which was developed by Liberato, we can look at how the ecosystem roles of different groups have changed over time. So in the historical version of the model, we see that the groups that were considered the most keystone were our sea stars and our lobsters. Now, if we fast forward to 2008, we see that the sea stars are still occupying this role, but we see that this ecosystem role of lobster has been diminished as a result of its reduced biomass. So this is really what we're interested in when we start asking these ecosystem questions about fisheries. So we explored this a little bit closer in sort of the first methods paper that we did for this LenFest research. And we were looking at trade-offs in invertebrate fisheries catches and ecosystem impacts in coastal New Zealand. And on the left, we have some plots showing the trends in the fisheries. So the number of invertebrate groups being fished in New Zealand on the left, so we can see an increasing trend. And we can see a dramatic increase in the landings, although this is quite variable from year to year, largely driven by variation in cephalopod catches. So within this ecosystem, we looked at the lobster fishery, the abalone fishery, which is locally referred to as Paua in the middle photograph there, as well as the urchin fishery, or locally referred to as kina. And this really is sort of the basis for the rest of the work that I'm going to show in this presentation. So the simulations that we ran with the ecosystem models, we basically simulated a range of different depletions of each of the individual species that we were interested in. So for this example, we simulated depletion of lobster at 100%, so local extinction. We also ran simulations with no lobster fishing at all, and then we also ran intermediate levels of depletion. So basically trying to capture the range of fishing mortalities that would be possible. The black line shown on this plot is the catch over the maximum sustainable yield. So if you were trying to maximize the catch through time, you would try to find the peak of that curve, which is often the case in single species management. But then we are also interested to look at the ecosystem impact that these different levels of fishing had on other groups in the ecosystem. And we measured this by the biomass of other groups that change by at least 20% of their biomass, or at least 40% of their biomass, shown here in the blue and the red lines. So we can see that as we increase the fishing intensity, we're having greater impacts on other species within the ecosystem. And that vertical orange line indicates the level of depletion that the fishery is operating at presently. So this is sort of the same methodology that I'm going to use for the rest of the slides. So of those three fisheries that we examined, lobster produced the biggest changes in ecosystem structure and function. And we identified a win-win scenario. If you decrease the lobster depletion, that vertical orange line, you could both increase catches and reduce ecosystem impacts. So now we wanted to scale this approach up and start looking at other fisheries and other ecosystems around the world. And we quickly noticed that these ecosystem models, which have a high demand for the amount of data, a lot of them kind of glossed over or left out invertebrates from the ecosystems. So we developed a criteria for models to be included in the study in order for it to be a rigorous study. So we wanted models that had been published in scientific journals, that had gone through peer review process. We wanted them to be fit to time series, so they were time dynamic. And we wanted them to include at least 3 invertebrate groups with fisheries. Now, I think there's something like over 1,000 ecopath with ecosystem models that exist, but of these criteria, there was only 12 candidate models that fulfilled them. So these are the model locations shown in the red dots here on this map, and we included the local ecosystem modeling expert as co-authors on this paper. So those are all the co-authors that are listed here. So we really wanted to have kind of the local expert to make sure that our simulations were realistic and that we weren't seeing something that was an artifact of the model. So in general, we repeated this methodology of simulating different levels of depletion, which is shown here LOD in the legend. So we have 25% up to 100% depletion, which would be local extinction. And then we looked across these different groups of invertebrates, so cephalopods, lobsters, crabs, and so on. And we found that fisheries for cephalopods and lobsters had the strongest ecosystem impacts in general. We also looked at the ecosystem effects by model, trying to ask the question, was there one model which was way more sensitive than the others and driving all of these kind of overall results? And we do see that the Great Barrier Reef and the Gulf of Thailand are a little bit more sensitive than the others, especially at the high depletion level there, 100% depletion. But in general, they were sort of on the same order of magnitude. We were also interested in looking at impacts by groups of interest. So how were birds and mammals impacted compared to all species within the group, as well as how were other commercial species impacted that were not being sort of simulated. And we can see that for commercial species, we see greater negative impacts through these invertebrate fisheries than we do positive. And we can see that these species of conservation interest are also impacted. Something else that we found that was kind of interesting was we noticed a strong benthic-pelagic coupling. So we were looking at the coupling between benthic and pelagic compartments. So for example, if we exploit a pelagic invertebrate through our simulations, shown in the blue colors there, we can look to see how pelagic invertebrates impacted pelagic fish. But what's interesting here is pelagic invertebrates actually had a larger impact on benthic fish. So we're seeing a high degree of coupling between these invertebrate fisheries and the effect they have on the opposite compartment. Now returning to this paper that I mentioned earlier, looking at the impacts of forage fish, there's been a lot of attention given to forage fish recently and really identifying that they play strong roles within ecosystems and their catches are increasing and we should afford special protection to them. We wanted to compare the general effects of invertebrate fisheries compared to these forage fish species which have been identified as being important for ecosystems. I'll draw your attention first to the right-hand side of the vertical axis. This is our kind of impact on the ecosystem metric, the proportion of groups that are impacted by at least 40% of their biomass. And the forage fish impact is shown in the gray line with the confidence intervals, and the invertebrate impact is shown in the red line. So the forage fish impact is higher, but the invertebrate impact is actually within the confidence interval. So we are seeing strong average impacts. If we look to the average catches or the MSY catches, we see here the forage fish catch in the blue line and the invertebrate catch in the green. And we can see here that invertebrates are more sensitive to fishing. We're seeing that we're achieving maximum sustainable yield at lower average levels of depletion than we are for forage fish. We also wanted to look at some different indices to see if we could sort of figure out generally if there are rules about what we can expect for ecosystem impacts based on the ecological characteristics of invertebrate events. And one thing that we noticed here is that most invertebrates, or many invertebrates, do not follow traditional fishery science predictions that only highly connected or highly abundant species will have high ecosystem impacts. So on the top plot here, we're looking at relative abundance. So invertebrate groups that have a larger abundance compared to the total abundance of the ecosystem would be on the right-hand side of the scale. And we can see, as looking at a rank of effect, we can see that even groups with small relative abundances can have strong effects on the ecosystem. And then the plot in the bottom, looking at the connectance of the invertebrate group, similarly, highly connected invertebrate groups, so this would be through their feeding linkages on the right-hand side of the horizontal axis. And we can see that even at low connectance levels, we can potentially have high impacts on the ecosystem. So this needs to be kept in mind when thinking about the impacts that we're observing. We also wanted to look at the resilience of ecosystems and to see if there was any kind of characteristics of not only the invertebrates, but the ecosystems in general that could explain the ecosystem impacts that we were observing. And while we didn't find extremely strong relationships, we did find two factors that we identified as influencing the impact. So we can see here connectance in the top plot on the horizontal axis. We see that as the ecosystem is more connected, we're generally seeing a decrease in the average ecosystem impact. And a similar trend for total ecosystem biomass. So as ecosystems have more biomass, we tend to see less ecosystem impacts as well. So this would be something to keep in mind if we're starting to think about the impacts of ecosystems as a whole. Now, the last thing I want to touch on today is ecosystem-based fisheries management, and starting to think about some different management targets that we might use at an ecosystem level rather than a single species level. So what are these fisheries management targets impacts not only on the target species, but also on the rest of the ecosystem? So this is a paper that Tony Pitcher published in 2009, evaluating ecosystem-based fisheries management performance of 33 different countries. And USA scored #1, Canada here #4, New Zealand #3. But interestingly, none of the countries achieved a good score. So even the best performing countries only achieved an adequate score. So we're interested in sort of exploring some of these different targets that have been suggested, such as this multi-species maximum sustainable yield target that was proposed in the Worm 2009 paper. So looking closely at two ecosystems, the New Zealand ecosystem that I mentioned previously, as well as one for here in Nova Scotia, the Western Scotian Shelf, that was developed by Alice Bundy and Julio Arujo. We wanted to start to simulate a multi-species maximum sustainable yield. So now we're not looking at an individual species level of depletion on the horizontal axis. We're looking at the level of depletion of the entire ecosystem. And the black line is actually the multi-species maximum sustainable yield, or the amount of fish that you're getting out of the entire ecosystem. So if you were going to try to optimize the multi-species maximum sustainable yield to try to get the most biomass out of the system, we noticed in both systems that this had really strong impacts on a lot of other groups within the model. So the red line is the proportion of groups that have changed the biomass by at least 40%. And we can see at multi-species maximum sustainable yield, we're getting between 40 and 50% of the ecosystem changing by approximately half of its biomass. Really strong ripples. So fisheries in both of these examples crash as operating as well. That's probably not a desired goal for local fisheries managers to collapse the most valuable fishery in both of these countries. This kind of puzzles us a little bit. Management target would collapse the most valuable fisheries as well as a lot of the higher trophic levels. So as a result of this, we came up with what we referred to as this safe operating space, which we've highlighted in green, in which none of the groups decreased their biomass by more than 60%. So I think we have to keep this in mind when we're thinking about these kind of ecosystem-wide targets. And there was a really interesting series of papers published in PNAS recently where they've looked at this in the East China Sea and observed that it maximize productivity in the system by removing the top predators. That you can do so with that is that your fishery is smaller. This had, in Nova Scotia, this had impacts on the resilience of the ecosystem. On the horizontal axis here, we have ecosystem level exploitation rate. On the vertical axis, ecosystem level of depletion. And we can see in New Zealand, this is kind of a relatively linear relationship. As we fish harder, we see that the ecosystem becomes more depleted. However, in Nova Scotia, we can see that there's kind of a step change here that's occurring at between 0.4 and 0.5 ecosystem level exploitation rate. So we're really seeing a shift in the ecosystem if we fish it above this level. And this resulting ecosystem was simplified and dominated by large catches of smaller species such as sculpin, mackerel, and herring. So these would be the situation that was kind of observed in the East China Sea in these recent papers. So this is the final slide I'm going to talk about here. Recommendations from all of this research. We think that there should be an inclusion and better resolution of invertebrate taxonomy within fisheries surveys. I know that this is happening in some places in recent years, but in other areas, it's still hard to get this data. More resources provided for invertebrate stock assessments for high value and high catch species. Increased resolution of invertebrate groups within ecosystem models. We would have loved to have been able to extend this study to a lot more models, but we were really limited to the amount of models that could work with asking these questions. The strong ecosystem roles played by invertebrates should be considered in ecosystem-based fisheries management policies. And in general, invertebrates are more sensitive to fishing and require more conservative exploitation rates represented in fishing policies. So with that, I would like to acknowledge all of my co-authors and collaborators who contributed time and modeling resources for this research, as well as the generous support provided by